All right, silly people, here's the situation. We have three spin one half particles um, in a box of side length L, um, which is pretty much a three-dimensional infinite square well. Um, and we're meant to find the energies um, of the first state, of the ground state, the first excited state, and the second excited state for these three particles, and the degeneracies associated with these energy levels. Um, so let's get into it. We can just write the Schrodinger equation, um, where the wave function will be a function of the position of the first particle, the position of the second particle, and the position of the third particle, which, and these are all free particles, so the Hamiltonian is just h bar squared over 2m, um, splitting up the gradients for each one separately like that, all times psi of x1, x2, x3 will be equal to the energies, the total energy E psi. Um, because the wave function is in theory separable, you can actually rewrite the wave function E psi, or just psi, I guess, um, as a convolution of three separable functions of x1, x2, and x3, which will be, I'm going to call u1 x1, u2 y, or x2, and u3 x3. Um, right, so that means that whenever you do the Hamiltonian, um, that the energy state for wave function I is just going to be minus h bar squared over 2m Laplacian I of ui of xi. Right? But that's just the um, one direction that you're looking at. So that actually has a known value as well. Um, that's going to give you h bar squared pi squared over 2ml squared, um, times the sum over j of um, nij, where j is the number of particles that you have in the system, in this case 3. Um, so to find the total energy of a given energy state, it'll be, I'm going to call it E subscript I, will be h bar squared pi squared 2ml squared. You have to sum over the dimensionality, so sum over I3, um, and then sum over the number of particles, which is also 3 of nji. Right. So the first energy state, which will be E1, this is the ground state, so all of nji are all equal to 1, right? Um, so you're hitting 1 9 times whenever you sum over 3 times, so it's just going to be that stuff times 9. I'm going to call that constant E naught, so I don't have to write it a bunch. Then E2, the first excited state, one of the particles will be in their first excited state, so n will equal 2 for one of the particles. hitting 2 3 times, and you're hitting 1 6 times. So it'll be 6 plus 6, so 12. Then the next level, two of the ends now are 2, while the rest are still 1. Um, so now you're hitting 2 6 times, which you're going to get 12, and you're hitting 1 3 times, so 3. So the next state is 15 E naught. To get the degeneracies for a given energy level, all you have to do is you need to find um, the spin degeneracy and the spatial degeneracy and multiply them by each other. Where the spin degeneracy is um, always going to be however many different possible states you can have for a given particle, um, which I'm going to label S, and then to the power of however many particles you have. So because we're dealing with spin 1/2 particles, which can either be either up or down, so 2 different states, and we're dealing with 3 particles, so 3 is d spin for each of these cases. Where the spatial degeneracy is always equal to the number of dimensions that you have multiplied by the number of particles you have, factorial, divided by energy state k times the same stuff up top minus k factorial. Putting all this in, you can get the degeneracy for each energy level. So the first one, the ground state, will have k is equal to 0. So the degeneracy d1 will be 8 times 9 factorial over 9 factorial, which is just 8. For the first excited state, where k is equal to 1, we have d2 is going to be 8 times 9 factorial over 1 factorial times 8 factorial. We're not actually going to calculate both of those factorials. We're just going to factor in 8 out of the, we're going to factor in 9 out of the 9 factorial, so that we just have 8 factorial over 8, which goes to unity, and then 8 times 9 is 72. For the next one, the second excited state, where k is equal to 2, we'll have d3 is 8 times 9 factorial over 2 factorial times 7 factorial. 2 factorial is just 2, so we're going to have 4, and then we're going to have to factor out a 9 and an 8 for the fraction to go to unity. So 4 times 72, 288. Sure. Then, okay, now we have to go to 4 particles and calculate the energy levels again. But we're going to be using the same formula as before, so do not fret. The only difference is now we're dealing with 4 particles, but still in 3 dimensions. Bah. So we're summing over the same amount of dimensions, but summing over just one more particle. Okay. E1, the ground state. All of the ends are going to be equal to 1. So what you're going to end up with is 12 E naught. The second, or the first excited state, one of the particles is going to be equal to 2, and it's going to be hit 3 times. So 3 times 2 is 6. And then the rest of the particles will each be hit 3 times. So 9, which gives you 15. And then the third guy, the second excited state, 2 of the particles are 2, and they'll both be hit 6 times total. So 6 times 2 is 12. And then the other 2 particles are both 1. They'll each be hit 3 times. So 6, which gives you 18. E naught. Then the degeneracies. Now the spin degeneracy, we have 4 particle. No, it's still spin 1/2. So we still only have 2 options, but we have 4 particles now, which is 16. And then the space degeneracy, 3 dimensions, 4 particles are going to have 9 factorial over k factorial 9 minus k. Wait, not 9. 4 particles times 3 dimensions is 12. 12 minus k factorial. Okay. E1. K is equal to 0. So D1 is 16 times 12 factorial over 12 factorial, which is just 16. E2, K is equal to 1. D2 is just 16 times 12 factorial over 1 factorial times 11 factorial, which is just 16 times 12 times unity, which is 192. 192. Then the degeneracy for the third energy state, the second excited state, K is equal to 2. D3 is 16 times 12 factorial over 2 factorial times 10 factorial, which the 2 will cancel out 16, so you have 8. Then you have to factor out 12 and 11 times 10 over 10. So you're doing 12 times 88, which is 1056.